All right, I'm going to do a quick screen share just to show you some of the wave functions we were just talking about. And I'll put a link to this simulation somewhere down there if you want. So I'm going to start out. This was the wave function we just described on the last board. And I believe that function was, let me just write that on here. It was psi 0 of x was equal to, there was some constant. Let's not worry about the constant too much here. We can figure that out in a workbook problem. E to the minus m omega x squared over 2 h bar. All right, so this is the wave function that you're looking at right down there. All right. Now, let's not worry about the time evolution, but we can actually square that. And notice right here, I'm on the wave function button. I can square that and go to the probability density and see what that looks like. So I'm going to go ahead and do that. Let's click on the probability density. And notice that makes it a little bit sharper peak. Okay, fine. And notice we're not really worried about the numerical values on the vertical axis. We'll figure those out. But for fun, let's go back to the wave function and see what happens as we go up in energy level. And so each of these different wave functions is going to correspond to different energy levels. And deriving those, these energy levels relate to those energy eigenvalues of the Schrodinger equation, right? So, all right, let's just see what some of these look like for fun and then stop this video. So let me get a couple of those things out of there. And then let's just start going up. So let's look at the second energy level. Notice there's one bump on the first energy level. And notice we call that historically E0 for the ground state. E1, which is the second energy level, if we start our numbering at 0, has 2 bumps, 3 bumps, 4 bumps, 5 bumps, etc. And so the energy level, like let's go up here to E9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Did I do it right? Something like that. 9 bumps. Oh, wait, because this is the 10th energy level because we started at 0. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 corresponding to the 10th energy level because, again, our first number starts at 0. So 9 corresponds to the 10th energy level. Watch out for that. You saw I just screwed it up too. Great. Now, what happens when we square this one and look at the probability distribution for this one? So when I hit the probability density function, notice we get this interesting part. And in this case, I guess I should mention something here. Wherever the function is 0, so all these spots where it's 0, there's 0 probability of finding the electron in those spots. It's most likely to be found wherever the distribution is tall, so right here and here. And this has to do with the fact that as you get higher up on the well, right, you're slowing down. You have less kinetic energy, so you're going to spend the most time at the edges of the well, so to speak. Now here I'm kind of glossing over something. We'll talk about this more in class. But basically, I hope this makes sense that as you get to the extrema of the oscillator, you slow down, you spend a little bit more time. We actually see slightly higher probability of being found far from the origin as the energy value goes up because you're spending more time far from the origin. All right, there's other, maybe what I'll do is I'll clear all these and I'll put a link to this in there. You should play around with this. This is super fun. But you can actually look at different, here's a Coulomb potential, right? We can look at the energy levels in 3D Coulomb. That's the Bohr model that we've talked about, right? We can look at these and maybe we can look at the wave function here to see more cool stuff. But you can see that there's all kinds of wiggles in these different wave functions and it just looks pretty cool. And we'll learn about these and study these in class. You can learn about a superposition state, which is in different amounts of each energy level. Like we could say something's in, let's go back to this quantum harmonic oscillator real quick. All right, so let's say, let's make a superposition state. This is where things get interesting. Oops. Can it let me, oh, I guess we can't do it with that one. My apologies. We'll go back to this one. Or was it 3D Coulomb? Maybe it was the square. All right, I'm having trouble. So I don't know what I did wrong here. But anyways, we'll mess with this in class, and I apologize. But anyways, I'll put a link to this simulation in there, and you should check this out. I'll figure out what I was doing wrong. We'll talk about it more in class. Okay, thanks.